All right, we are now recording from current slide. Seemed like we were past that. Yeah, we were way past that. One slide away. Okay, let me go over the announcements. You've heard most of them before. If any of you are interested in being on the math team, Mr. Rossi is meeting with them on Fridays at noon, Birmingham West Campus, the Science Building, which is C Hall C100. That's the first door on the left when you're coming from the library building. You go past those stairways there, and then you're in there right when you go in the hall on the left. And then they meet again on Monday afternoons at 3. Tutoring is available on this campus, but down the hall here in room 202. That's the SSS tutoring lab. If there's no full-time person in there, go all the way down the hall, take a left, and go to room 212 and ask for Ms. LaSharon Harris, or maybe your secretary can help you line up there. Now, downstairs in room 105, they also have tutoring in the Space Center, and so those are 2 opportunities if you need them. Now, if you're doing pretty well in courses, you may actually qualify to tutor, so give that a consideration as well. All right, and then the one last announcement is, it seems like every week I've been saying this recently, but I normally have office hours on the Birmingham campus from 7:45 until 11:45 on Fridays. My biggest chunk of office hours left now the second mini-term has begun. And again, this Friday, I've got a doctor's appointment. Now, it's my annual physical. I don't know how long it's going to take. I think I'm near the front of his queue, so hopefully we won't have any backlog. If there is no backlog, I might be able to get to the Birmingham campus mid-morning. I don't know. But if there is a backlog or things that they have to check out or whatever, then I won't be there at all. Okay, so, and then I think there's a meeting called sometime for tomorrow too, so even if I'm on Birmingham campus, I may not be in the office, but I'm going to try to get over there, but we'll see how it goes. Okay. After this, I think it's only going to be one Friday a month that I'm going to have treatment, so I'm through with the once a weeks and every other week, so I'll be going to once a month now, so I'll have one treatment in April, one in May, and the May probably won't affect this class at all, and then one in June and July, I believe. So getting closer to being through with those. All right, we have a new person in the class, so let me go over just a few things. Not been in one of my classes before. So we've met. This is our 4th meeting. So we've had 3 already. And by the way, if you saw what I was doing before, right now I'm recording, okay? And sometime tomorrow, I don't know what time tomorrow, possibly tonight, but I doubt it, it's going to upload to YouTube, okay? And yeah, I think I forgot to tell the rest of the classes too, so let me go and get this done too. Are you familiar with Blackboard? Okay, when you go to Blackboard, the home page of Blackboard for this course, in the upper left corner there's a series of tabs. And something like the second or third or somewhere in there tab is one that's called Content. If you click on that, you'll see several things come up. The first you'll see is, and there's Miranda. Okay. There you are. All right, has anyone else come in since I called roll? Okay. Now, under Content, you'll see the syllabus. Now, you can read through the syllabus. I think I've updated and got everything correct in that. The next thing you'll see is the research paper general instructions, and you can read those because there is a research paper due. Yeah, someone pointed that out to me today. I didn't have a chance to go back there and see it.
Thank you, sir.
Okay, glad to. All right. Research paper general instructions. The research paper is due, not optional, is due by the end of the term. Better to get it in earlier rather than later. I've received maybe one or none from this class. One from this class. Very good paper. Okay? So, get them in early rather than putting them off. Then you'll see my locator card, and that shows when I'm in class, when I'm not in class, when I'm on campus, when I'm not on campus, which campus I'm on, that kind of stuff. You'll see that next. And then you'll see the PowerPoints for each one of the classes here. And JJ's here. All right. And those are just static, just the PowerPoints as you see them. Earlier, I couldn't get, I think, past Chapter 4 to load. More recently, I have gotten all the rest of them to load. Okay? Josh, right? Okay. And there's Travis, right?
Yes.
Okay. Anyone else come in since I called roll? All right. So then you got all the PowerPoints. The very last thing in that content list is one that says, and I didn't have this set up before either, but I've gotten it set up now. It says PHS112 YouTube videos. You know, Physical Science 112 YouTube videos. If you click on that, you'll see the previous 1, 2, 3 classes that we've had. They're long videos, by the way, about 4.5 hours each, or close to it. I do shut it down if nothing's happening in lab, say, or we're on a break or something. So they're not 4.5 hours, but they're pretty close to it. So that first day of class, you'll hear me not just see and read the syllabus, you'll hear me talk about it. Okay? You'll not just read what the research paper is, you'll hear me talk about it. You'll not just see what my locator card, that kind of stuff, I'll talk about it. Then we also talked about safety, what to do in case of weather emergency, what to do in case of fire or internal, chemical spill, something like that, emergency, and also what to do, unfortunately, in case of active shooter. Unfortunately, these are coming closer and closer to home here. Last night, I was driving home from the Birmingham campus because I had a physics class there last night. So it was about, my class was over at 6, so I was on the way home between 6 and 6:30. And there were, on the interstate, there were 2 or 3 police cars, blue lights flashing, just racing down the interstate, and people were getting out of the way. They were weaving in and out. I thought there was going to be an accident with them. They got off right ahead of where I was going to get off, and turned out there was an active shooter at UAB Highlands Hospital. Killed one person, killed himself, and injured another. That's the last I heard. So, and then Huffman High School had one, a couple weeks ago. Yeah, this is bad. But anyway, we talked about what to do in case there was one here. So those safety things are there, okay? And then we started Chapter 1. Then the second class, we finished Chapter 1 and had the lab in Chapter 1. And then the third class, we started Chapter 2 the second time. We continued in Chapter 2, had the lab in Chapter 2, and the test in Chapter 1. So there's 2 labs and 1 test. Sometime you'll need to get caught up on. I've got copies of them, and we're going to have another lab today if we get enough cover. So there's quite a bit to do. So understand that. All right, any questions on anything we've done so far, where we're heading, that type of thing? All right, just a little bit of review. In Chapter 2, we have been talking about motion. That's the title of the chapter. And we talked about several aspects of motion. Distance and displacement, distance being a scalar quantity, just a number, a magnitude, displacement a distance with a direction, the vector quantity. Okay, then we took the time rate of change of that and came up with speed for time rate of change of distance, velocity for time rate of change of displacement, vector quantity, speed a scalar quantity. Then we took the time rate of change of that and we got a velocity and we got acceleration, typically a vector quantity. Okay, and pretty much leads up to where we are now. Okay, and we did some other things like uniform acceleration, those kinds of things. Today we start off with forces. And we'll talk about forces and then go back to motion. Now, I don't understand their organization here, but that's what we'll do. So we'll talk about, following the book, talk about forces, then we'll go back and do horizontal motion on land, which is sort of similar to what you did in lab last time, except it wasn't strictly horizontal, but it was one-dimensional motion. You kept changing the elevation, but it was one-dimensional motion. Then we'll talk about one-dimensional motion downward, that's falling objects, okay? And then we'll talk about compound motion. Now that's what I hope we get to cover today. That's 2.5, because that's what the lab is on today. So if we can get that far, we'll be ready for that. Then we go to 2.6, which is the three laws of motion, which is again forces, okay? To me, this force section here really would be better waiting to do it there. But we'll talk about forces now, and then we'll get the horizontal motion, vertical motion, and compound motion covered. Then we'll be ready to go about the three laws of motion, which involve forces, Newton's laws. So let's start with historical background here, forces. Aristotle, way back, like 3rd century, 2nd, 3rd century before Christ, way back, ancient Greek, but a brilliant philosopher, okay? That's what they called scientists back then, natural philosophers, even though science wasn't really a field yet. He, and we've talked about this before, basically did thinking, okay? He looked at nature, observed nature, and then came up with conclusions. He never tested his conclusions, okay? And just looking at things, he said, oh, well, of course, heavier objects fall faster than lighter objects, right? It sort of seems like it would make sense. If I held a ping pong ball and a bowling ball and dropped them, bowling ball is going to hit the ground first, okay? So heavier objects fall faster than lighter objects, or so he claimed, okay? Also, he said that objects moving horizontally require continuously applied force or else they come to a stop. And sure enough, on the surface of the earth in the most normal conditions, that's the case, okay? Things just don't keep moving indefinitely. But he said they require motion, additional applied force, or they come to a halt. It seems to make sense, okay? But he did all this relying on thinking alone, okay? Now, hopefully you remember who came next. Galileo and Newton, okay? And this is 200 or 300 BC, and moves felt forward to what was about 1500 AD. Okay, so quite a while later, Galileo especially started off saying, is all this really true? Because up to then, if Aristotle said it, everybody swallowed it. Hook, line, and sinker, didn't question it, didn't test it. Galileo said, some of these things don't quite make sense. Now, I don't know if he did this one, but if I push this chair across the floor, sure enough, after a while it will stop. But if you were on a pair of ice skates and could stand on them without falling down, and I pushed you across a ice rink, you don't stop nearly as fast as the chair does. Okay? Same push, same everything. You glide and just glide. Okay? Almost seeming not to stop. So there's something else involved. It's not just that the horizontal force is required. That's just one. Another thing he did, or at least tradition has that he did, he lived in Pisa, Italy. What's the most famous building in Pisa, Italy? Say again? The Leaning Tower of Pisa. Okay? It's not P-I-Z-Z-A, it's P-I-S-A. Coco is here. If I can find you. There you are. And supposedly, he went up, climbed up the Leaning Tower. Now, I've seen a cartoon on this. He went on the downside, not the upside. Dropped it, bounced down, and said, something's wrong here. No. He went to the other side and dropped a very heavy rock and a very light rock. And they hit the ground at the same time. Okay? And he said, something seems to be amiss in the logic here. Okay? I'm going to show another illustration of that same thing. I wish I had some worse paper than this. I think I will use this one. Got plenty of paper. Ah, here we go. I don't have to use that. Okay. All right. Here's another way of looking at it. He didn't do this one, but it's another way of looking. These two pieces of paper, would you say about the same weight? Yes. So they should follow about the same rate, right? According to Aristotle, right? According to Aristotle, they should follow at the same rate. Okay? Now, am I adding any weight to it? No. Still has the same weight. Heavier objects fall faster than lighter objects. So they have the same weight. No, they didn't fall at the same rate whatsoever. What was the difference there?
Surface area.
The surface area. That's the key. It wasn't the weight. It was the surface area. Okay? So, Aristotle, off a little bit. Okay? Now, that's just another. There are several other things that came out. So Galileo and Newton changed this around and started thinking in different terms. Okay? And they concluded all objects fall at the same rate. Unless, of course, you've got some surface area or other kind of problem in there. If all conditions are the same, they do fall at the same rate. Now, we actually did this little demonstration back when I could get into it, but the old physics lab was down at 259, and that's the only part of the building, that lower part down there, that actually has 3 stories. And in the back corner of the old physics room and lab was a door that I got somebody to open. I didn't have a key to it, and they did, and it's a stairwell. No one uses it. But it was a stairwell there, and I could go up to the 3rd floor, and that's the highest floor in the building. And I had a 1 kilogram mass, 1,000 grams, and a 1 gram mass. Okay? I went to the window there at the top of the stairwell, held them out. The class was down there. I said, okay, which one's going to fall fastest? Aristotle would have said the heavier one for sure. It's 1,000 times heavier. I dropped them. They landed at the same time. Okay? And that's just 3 stories, but I didn't have the Leaning Tower of Pisa to do, but yeah, it did work out the same way. All objects do fall at the same rate, unless there's some other mitigating circumstances. If all conditions are the same, they fall at the same rate. Now, this is the one that it doesn't seem right, but it still is. No force is required for uniform horizontal motion. No net force is required for uniform horizontal motion. That net is an important word there. Okay? And what they did was reasoning based on measurements. And Galileo particularly, what he was doing was rolling balls up and down inclines. Okay? And similar to what y'all did in lab last time, and somewhat similar to what we're going to do in lab today. Okay? And he did it based on measurements. Now, back then, there weren't any good clocks. He was using sand through an hourglass or something. There weren't any clocks that you use for timing and stuff like this. It was a pretty rigorous, but he made the measurements, and later Newton formed the theory. Okay? So let's look at forces now, even though we're going to come back to this after we deal with our motion, more motion. And here's the concept. A force is, or one definition of a force, is a push or a pull capable of changing an object's state of motion. Now, what are 3 ways we could change an object's state of motion? Second?
Speed it up.
Speed it up, for sure. Or slow it down. Or turn it, change its direction. Absolutely, those are the 3 things. And anything that's capable of changing that object's state of motion, that would be a push or a pull, and that would be a force. Okay? Now here's an example. This looks like a cargo ship. I was on an ammunition ship where we had some sister ships that look fairly similar to that. And, when a ship is coming into harbor, big, bulky ship like that, they can't maneuver all that well in very tight conditions, so they usually bring in tugboats. Okay? And if you brought in 2 reasonably sized tugboats, and both of them pushed on this side of the ship, then with 1,000 units to the east, then the net force on this ship would be 2,000 units to the east. If that was the only force on the ship, that would be a net of 2,000 units to the east. Now, if they got their wires crossed, and one was on this side of the ship pushing with 1,000 units, the other one didn't know where that guy was, but thought he was supposed to be pushing on that side, but they couldn't see each other because the ship's in between. What's the net force? 0. Even though they're both pushing like crazy, the net force is 0. Okay? Now, what if there was one that was pushing at 1,000 units of force to the east, but then the second one was on the other side of the ship, couldn't see it, and pushing with 2,000 units to the west? What's the net force? 1,000 to the west. This tug over here, what is going on here, I'm pushing as hard as I can, and yet I'm getting pushed back. Okay? That would be a net force of 2,000 units to the 1,000, net force of 1,000 to the west. Okay? So a force is a push or a pull capable of changing the object's state of motion. The overall effect is determined by the vector sum. So the directions definitely matter here of all the forces. In other words, the net force on an object. All right. Joseph, right?
Yes, sir.
Okay. Anyone else come in since I called roll? Okay. So we're still missing Alexis, Justin Hay, and Lauren. The ones that have typically been here. I have some others that have never been here. Here's another example of this. This is one we actually did. When we first moved into the house where we currently live, it had a nice wooded yard. Our previous house had no trees at all. We had a little shade from the neighbor's tree and a little shade from a corner where a scrub tree had grown up. But no trees, actually. We planted a few things like crepe myrtles and things, but it was a really small lot. So when we moved into the bigger house, bigger lot, had lots of trees. In fact, it really had too many trees, okay? We had, in this one area of the yard, a big pecan tree, pretty good size, up there on top of the hill. Near it was an oak with a really good size. There was a little maple trying to make its way between the two, and it wasn't doing too well. We took that one down. And then there were two little pine trees. There were two big old pine trees that had been there forever, still there, and another oak or two, and a big oak over here. So, yeah, there's lots of them. But two little scrawny pine trees that were trying to make their way up to find some sunlight. And they were crooked and just really ugly little trees. Tall and spindly, ugly little trees. So we thought we need to take those down too, but they were so tall that we were scared they were going to damage other things when they were doing. We didn't want them going toward the house. We want them going down the yard where there wasn't anything to bother. So my father-in-law and brother-in-law came down from Huntsville, bringing a chainsaw and some rope or line. And what we did, we took the line and threw it as high up in the scrawny little pine tree as we could. Finally found the limb up there that we could wrap around, so we had it. Now, my father-in-law was operating the chainsaw. It was his. My brother-in-law and I were going to be pulling on the rope. It was around the tree, and that way we could guide it down to where we wanted it to fall. It would be falling back toward the house. Now, to get the maximum net force, we would have each had an end of the rope and pulling back this way. Then our two forces would be, those are pulls or forces, would be pulling the tree this way. What's wrong with that picture?
That's where the tree's falling.
The tree is going to fall dead on top of us, okay? So what we did, we spread out, of course. We were about to have that happen, and then we pulled, but then we didn't have as much net force pulling. Because if you think about it, remember, forces are vector quantities, okay? And let's see. Let me get my pen activated here. Okay. So if one of us was pulling this way and one of us pulling that way, okay? And we're wanting the tree to fall basically that way, and that the direction it fell. Notice with me pulling this way, I have one component of the force in this direction, another component in that direction. With Dan over here pulling, he had one component in this direction and one component in that direction. Well, these two components basically cancel out. One's positive and one's negative. They cancel out. You can add these two components together, and that's your net force in this direction, but these cancel out. We were willing to risk that, have pulling against each other to keep from the tree landing on us. Okay? Now, my younger brother works for he's retired now from a electric power company, rural power company, and he's always driving by looking at the power poles, even of competitors and stuff. He's fascinated with power poles, so he's got me looking at power poles too. And you need to look at them sometimes because you can see a lot of physics there. Up in Winston County, my wife's family had a lake place up there, and when my parents-in-law decided they were going to build a retirement home, they were going to liquidate all their assets, but they wanted to keep the lake place in the family, so they said, "You don't have any kids, you're buying it." Yes, sir. Yes, ma'am. Okay, so we wound up with it. So we are up there. You ever been there? The roads sort of go like this, okay? And the power lines have to go like this too, okay? They try to keep them as straight as possible, so The road may go underneath the power lines like this, but they still have bends in them. And everywhere there's a bend in the power line, what do they have to do? Put a guy wire here to keep the trip. Because if you didn't, the wire's here, the wire's here, the pole, power line pole is going to bend. So they have to have a what they call a guy wire out here, fixed in the ground, really deep there, and with a lot of tension on it to keep the poles from bending over. Look at that. It's net force. They want the net force on that pole to be zero. The wire is pulling this way, this there. The guy wire is pulling in the opposite way. The net force, in order for the pole not to bend, is zero. Okay? Physics is everywhere. All right. Now, those are all the forces. There are four what they call fundamental forces. Now, why they have this slide in here, I'm not sure. We're not going to deal with any of these. But just to let you know, there are these four fundamental forces. And we are dealing with this one, of course. The most basic of all the interactions are, first, gravitational. These are mass interactions. Okay? The reason I'm standing here and not floating off is because the mass of the Earth is pulling me downward. Okay? And this same mass works on the planets, the stars, galaxies, solar system. Everything is operated because of that. So gravitational forces are really pretty strong forces. And on the other hand, they're not. But they go long, long distances. I mean, across our galaxy, the Milky Way is like 100,000 light years, which is how far light travels in a year when light travels at 186,000 miles per second. Multiply that by 60 seconds. That's a huge number, well over a million miles per minute. Multiply that by 60, you have how far it travels in a hour. Multiply that by 24, how far it travels in a day. Multiply that by 365, that's how far it travels in a year. That's a long, long distance, okay? And that many light years, 100,000 of those, is what the diameter of our galaxy is. The gravitational forces act that far, or at least half that far, from the center, the black hole that's in the middle, to the farthest out there star, and beyond. Okay? So gravitational forces, we feel like they're fairly strong, they're really fairly weak, but they go long, long, long distances. Okay? They're mass interactions, just the activity from one mass to another mass. There's another type of force, and we'll do this in Chapter 6, electromagnetic forces. These are charge interactions, not mass interactions, and they come from both electricity and magnetism. Okay? I don't know if you've seen this little illustration. If you take, say, a piece of paper, break it, tear it into tiny little, little bits of paper. And then with a rubber comb, for those of you who have enough hair to do this, I don't. Okay. But comb your hair with the rubber comb and then reach down and you can pick up those little pieces of paper. Why? Okay? Because when you comb your hair with a rubber comb, it takes electrons off your hair, embeds them on the comb. I believe that's the way it goes. So the comb becomes slightly charged. I mean, very, very little charge, but it'll pick up little pieces of paper. So, well, guess what? Those little pieces of paper, without anything else, gravity's pulling them down. So that electromagnetic force, electrostatic force we call it, is actually stronger than gravity because it raises them. And sometimes you'll get a little chain of them there, okay, because of the charge interaction. So believe it or not, electromagnetic forces are stronger generally than gravitational forces, but they don't act for nearly as long, as great a distance. Okay? Now, that involves atoms, molecules, and chemistry, because you're knocking electrons off of one material onto another material, and then you have a charge difference, and that charge difference is what attracts the electromagnetic attraction. Now, within an atom or a molecule, you have some weak forces that are involved in certain nuclear reactions. Now, we're not going to do any nuclear reactions. No nuclear explosions in this class at all. Okay? We're going to avoid those like the plague. Okay? But these weak forces are much stronger than the electromagnetic forces. For instance, how is an atom composed? Okay, protons, neutrons, electrons. Where do the protons live? Say again? Did I hear something? Where do the protons live? In a nucleus. Okay? A tiny, tiny, tiny little nucleus. How about the neutrons? They live in there too. How about the electrons? No, they're in a cloud. I mean, an enormous cloud relative to the nucleus there. Well, here you have these protons that are all positively charged, all living in a tiny little nucleus. Why is that not blowing apart? Because the weak forces are holding them together. Now, we don't, well, maybe quantum mechanics know and understand a little bit more of how that actually works. But yeah, they are far stronger than electromagnetic forces, which are much stronger than your mass interactions, your gravitational forces. And then you have the strong forces which hold the nuclei together, which maybe you can classify some of those as those two. So it's these things, we're not even going there. But those are the four fundamental forces that are beyond the much stronger, in increasing order of the strength here. All right, Lauren, right? I'm sorry? I'm sorry, I saw you earlier. Alexis, I'm sorry. We still haven't seen Lauren. Okay. I thought I had already marked you here. Sorry. Okay. And basically, that's all we're going to do with these forces. Just talk about them a little bit and move on. And here's the moving on. Okay. That little blurb was forces. Now we're forgetting about forces for now, and let's talk about horizontal motion on land. We're not totally forgetting about forces. But I guess they said it because here you're going to be having forces all over the thing, so they had to define what they were, push or pull. So let's talk about horizontal motion on land, or it could be on the floor, or on tabletops, or whatever. Horizontal motion. Back to Aristotle's natural motion question, is a continuous force needed to keep an object moving? And we said sort of it depends on what your surface is. If that's the ice rink, you don't need a lot of force to keep it moving. Once it's moving, it's hard to stop. That's one of the things I hated most about, there's many things I hated about ice skating, but one of them was, it was hard to stop, okay? Especially if you got moving pretty fast. Now, people know how to do it and all like that. I didn't. I tended to fall most of the time. So, not a good idea, okay? So, don't need a lot to keep moving, okay? No, and here's the key. I said this earlier. In the absence of unbalanced retarding forces, no, you don't need that. When I push the chair across the floor, and it does slow down and stop, wait a minute. Did y'all hear something there? When I pushed the chair across the floor, did you hear something? Were you hearing something? Yeah. Okay. What was that you were hearing? The chair all went across the floor, yeah. Well, why were you hearing something? If that was ice on ice skate, you don't hear much of anything, do you? You were hearing something because there were vibrations going on. You had friction between the wheels and the floor, and that's what's making the noise. Okay? Because there was friction, that was an unbalanced retarding force that was slowing the chair down. That was me pushing on ice skates across there and watching them fall. No, then that would not have been making noise except when he yelled and landed. Okay, so no, in the absence of unbalanced retarding force, no, you don't need a continuous force to keep things going. Okay, so here's sort of what they're talking about here, and looking at it from the other angle. If you push the chair or roll a ball or whatever it is across the floor, you have, actually you're pushing it this way, okay? It's rolling this way. But as long as you're not adding any applied force, the chair, also, now this one you didn't hear too well, is hitting air molecules. And that's tending to make it stop. Now, that's not a huge amount, but you saw the difference here. The air molecules were keeping that sheet from falling as fast, okay? Because it was hitting more, because it had more surface area, okay? So you have the force of the air molecules pushing back. The friction between the wheels and the floor were pushing back. So even though you had motion in this thing, gradually these forces overcome zero and they make it stop. Okay? Now, if I did an applied force, okay, and I kept just a little force on it, so you have a constant speed here, I'm still touching and just barely pushing, motion continues. Well, the force I was exerting is equal to, but opposite for those retarding forces, the ones friction and air resistance. Okay? So that's what this is illustrating. If you do have an applied force here, and this is what Aristotle was looking at. He said you have to have a constantly applied force to keep continuous motion, because he wasn't taking into account the unbalanced retarding forces that he couldn't see happening, but it was friction and air resistance in general. Now it does move at a constant velocity because you have the applied force equal but opposite to the retarding forces. So the sum of these two is equal to that. Your net force is zero. And what does net force of zero mean? Net force of zero. Say again? Okay, it may be. Net force of zero on the chair right there, it's not moving. But it also means, say again? Okay, equal forces, that's net force of zero. But if I'm pushing this at a constant speed, I still have a net force of zero. What a net force of zero means is no, and we're going to get to this later, no acceleration. Just the fact that I'm moving at a constant speed, the net force is still zero, okay? Because there's no change of motion. And certainly if it stops, there's no change of motion. But if it's going in a straight line, constant speed. Did we talk about the airplane before? Did I give that illustration? No, okay. We'll hold off on that and do it later. Okay. Inertia. Inertia is a measure of an object's tendency to resist changes in its motion, including being at rest. Okay? This chair has a certain amount of inertia. It takes a certain amount of force for me to make it change its motion. The desk here has a lot more inertia. It's a lot harder for me to change its motion than it was for the chair. Also, it's flat on the floor. The chair has wheels, several things there, but it's more massive, okay? Inertia is a measure of an object's tendency to resist the changes in the motion, including the being at rest, okay? Now, any of you baseball players or fans of baseball? Okay. Now, do you remember, I'm not even sure who the fastest pitchers are today, but back in the day when I was following more, Roger Clemens, Randy Johnson, way back before that, Bob Feller, some of those guys, they really threw hard, very hard. And the poor people who had to catch them at those kinds of speeds, they had to have pretty sore hands at the end of the day, because you are having to change motion of that baseball. It's coming at you really fast, you have to bring it to a stop. Okay? Now let's just imagine that they were throwing bowling balls and could possibly throw them that fast. I'm not even getting back there, okay? I'm not going to catch Bob Feller or Nolan Ryan or those guys, but I'm sure not going to catch a bowling ball coming at the same thing, because it has even more inertia than a baseball does. Ping pong balls, no sweat. Okay, I'll be back there to catch them as fast and hard as you want to throw. Okay, I'll manage that. Okay, so inertia is the measure of the tendency to resist a change in motion. Now, I'm sure you've had experience somewhat similar to this, but a few years ago, several I guess now, my lawnmower was, I guess the ethanol gas had eaten away at some of the plastic tubing in it, and it was spilling gas, dripping gas out of the line. And soon I couldn't mow the yard on a full tank of gas because it was leaking all the time. So I had to go get it repaired, okay? And put it in the back of the pickup I had at the time. And thought I had chocked the wheels well enough, but then I found out that when I took off, I heard bang. And when I came to stop, I heard bang. What was going on there? Say again? Why was it moving? Because the truck was changing its motion, and the lawnmower's inertia was trying to keep it going in the same direction. So when it was at rest and I took off, bang, it hit the back of the truck, because it was trying to stay where it was. Its inertia was trying to resist the change of motion that the truck had. And then when we were going along at a constant speed, it was happy, I was happy, the truck was happy, everything happy, until I came to a stop, and then bang, it came into because it was trying to maintain its resistance change of motion and keep going even though the truck had stopped. You ever ridden a bus when there were no seats? You're hanging on? And it works on the trains too, especially in Atlanta Airport. If you've ever been there, you know, you better hang on, because those things take off in a hurry and they stop in a hurry. Okay, buses maybe not as fast, but it still happens. And if you're not holding on to something, if you're not paying attention, when it takes off, you're going to sit in some lady's lap back. Well, yeah, it's not going to be good for her. Okay, and or when it comes to a stop, you're going to be thrown forward because you are trying to resist the change in motion. Same thing happens when it turns. We say, I got thrown into the side of the car. No, I didn't, or side of the bus. It cut in front of me. I was trying to maintain my motion, it changed. And therefore it felt like I was being thrown to the side. But in reality, I was trying to keep going straight when it cut in front. So I hit the side. So that's what inertia is. Now, let's talk about the differences between balanced and unbalanced forces. Motion continues unchanged without unbalanced forces. So if an object is moving along here and there are no unbalanced forces, it's going to continue moving that way. Okay? Before we get to the spacecraft, and there's a reason we use a spacecraft, let's go to the airplane. You said I didn't do this. What if we had an airplane, a jet airplane, a great big old passenger jet airplane, flying along in nice level flight, 500 miles per hour, okay? Flying in nice flat level flight, 500 miles per hour, constant speed, 500 miles per hour. What's the net force on that plane? 0. Because it's not speeding up, it's not slowing down. Does that mean there's no forces on the plane? It's a big, heavy jet full of passengers. You think the Earth's not pulling down at it? Of course it is. But it's not falling because it's flying at nice level flight. Now, you may not understand how. Have I given this illustration before? The piece of paper and blowing? Did I do that one? Did. What's going to happen if I blow under the piece of paper? Yeah, it flattens out. What happens if I blow over the piece of paper? Nothing? Okay. Uh-oh, it comes up too. All right, now what is going on there? Okay. There is a feature in, and I think I may have mentioned his name before, it's called Bernoulli's effect. And you've all experienced this before, I'm pretty sure, that when a fluid, now remember a fluid is not just a liquid, it's also a gas. When a fluid increases its speed, it decreases its pressure. Okay? An object moving in a fluid, when it increases its speed, it decreases the pressure. So that's what's happening here. Now, what's happening when I blow under it, of course, the force of my blow is pushing the paper up. That makes sense. But when I'm blowing over the top of it, the speed of the air on top, since I'm blowing, increases. So therefore, there's nothing that it hits against. So it decreases the pressure and pulls the paper up. If you have ever thought about it, that's why that big multi-ton plane can fly. Because if you look at its wings, there's two things going on there. First, they're tilted down like this, so there's air going to be bumping here, but that's not going to be enough. They're also rounded across the top and taper off at the bottom. That means the air going over the top has the, okay, starting here, the air is here, the air is here. The plane goes in between. The air over the top of the plane speeds up because it has further to go. The air underneath actually slows down because it gets into that. But overall, and that's called lift. Exactly. Bernoulli came up, there was a whole family of Bernoullis. It was Daniel Bernoulli, who was the son. There were the two brothers, Jacob and Johann Bernoulli. They fought like cats and dogs, but they got along sort of okay. They were brilliant mathematicians and physicists, Swiss, I think. But then one of them had sons, and one of them probably was Daniel. And they were really bright too. And this one time the dad, one of the dads, I think it was Jacob, had entered this big math contest, knowing he was going to win because he was the sharpest thing going out there. He didn't know it, but his son entered it too, and actually did a more elegant solution to the problem than the dad did. They announced Bernoulli won, and he went out there, nope, Daniel Bernoulli, or the other one. And he got so mad at his son, he kicked him out of the house. Okay, I mean, they just didn't get along too well sometimes, but they were brilliant people. Well, Bernoulli, they were physicists and mathematicians, so Daniel Bernoulli came up with that, and that's why planes can fly. So you have gravity pulling down on the plane because it's massive, but then the lift from the air going over the wings. And by the way, if you think about it, what's the plane doing when it's going down the runway? Picking up speed. So the air going over is going faster and faster, and after a while you get enough that it lifts. The air going over the top, the pressure is less, more pressure on the bottom, and it goes. So if it's flying along at constant speed, net force is zero, the weight pulling down equal to the lift of the wings picking up. But then also you've got these jet engines firing exhaust out of the back. Shouldn't that be, yes? I'm sorry. Oh, okay, thank you so much. See, my dedication to be with you guys, I wasn't there to get whatever. Okay. Y'all are important. Yeah. Makes you feel warm and fuzzy, doesn't it? Okay. So, you have the jet blowing exhaust really fast out of the back, which is pushing the plane forward. So why isn't it speeding up? Because it's hitting all that air resistance. 500 miles per hour, that's some air resistance. Now, I did this when I was a kid, sort of a dumb thing to do, but I just felt so neat about it. When we were driving down the road, my dad wasn't looking, and we never had air conditioning in the cars. Teenager, no, I think I was in college before they bought a car with air conditioning. So we always had the windows down, summertime or spring or something. And when I could, I just loved putting my hand out the window and feeling it just yank my arm back. Now, at slow speeds, I could do it out, keep it there. But boy, when he was going 60 or so, I don't know why that felt so cool to me, but I did it. So going at 500 miles per hour, I think it'd have taken the arm off, separate the shoulder or something. So yeah, there's a ton of air resistance when you're going at 500 miles per hour. And that's why they still have to have the jet engines roaring away, because otherwise the air resistance would slow it down and would come to a stop. So the net force is zero, though the forces are all over the plane. Gravity pulling down, lift pulling up, air resistance pushing back, jet engines pushing forward. But yeah. So now let's go to outer space. Okay, way out in outer space. So there's no gravity to speak of, and there's no air resistance to speak of, so it's just out there, okay? Natural motion in free space means that that satellite is just moving along, constant velocity, no change of direction, no change of speed, not falling, not lifting, going along at a constant rate, okay? Now, if you had some retro rockets on it that you fired in this direction, meaning pushing back this way, what's that going to do? Slow down. No, slow it down. It was moving this way. Fire them this way is going to slow them down. So that is going to change the motion. You have a net force acting on the satellite. Okay? If, however, you would have had the retro rockets this way pushing it forward, what's it going to do? Speed it up. Just like you said before. But if you have the net force at an angle here, what's it going to do? Change its direction, make it turn. May not change its speed at all. In fact, that would not change its speed, but it would change its direction. So all the three of those are net forces that change the body's motion. The motion continues unchanged without the unbalanced force. When you do have the unbalanced force, it's either going to decrease speed if it's retarding, that was the first one, increase speed, that was this one, if it was in the same direction, or sideways force changes its direction. And sometimes doesn't even change the speed at all. All right, make sense? Okay. That was it for horizontal motion, okay? I thought there might be a example, but there's not. There is this myths, mistakes, and misunderstandings. Some of these are a little weird and sometimes placed at weird places. This one, a little bit strange. It says, what should you do if you're caught in the rain? Are you going to get wetter by walking, by running? What should you do if you get out there and a storm comes up, it starts raining? What should you do?
You should run even though you're going to get wet.
Say again?
Run even though you're going to get wet.
Okay. If you run, a couple things are going, and this is all in this, and I don't know why they have it here, but your front side is going to get more wet, and the back side, if you're running forward, is not going to get as wet. You've noticed this probably when you're driving down the road, right? Your windshield, if you're driving down the road, the rain is really hitting there, and your back window is hardly getting wet at all because you're going. But really, the total wetness, if you're running, you're going to be out there shorter time than if you're walking. If you walk the same distance, you're going to be out there longer. You'll get wetter walking. So that's usually why we run. Why it's here, I don't know, but Interesting little thing to do. Okay. So now let's move to falling objects. Again, this is straight line motion. Horizontal motion is straight line motion. Falling is straight line motion. There is a difference, though. Anyone know what it is? Say again? Okay. Horizontal motion, especially if we'd had no friction here, I push and it just keeps moving at the same speed forever. Same thing happen if I drop it?
You got gravity.
Oh, you got gravity. You do have a net force. There, you see the gravity is pulling down this way, and the floor, though, is pushing up this way. So you have no net force vertically. So when you push, it's going to roll, But when you drop it vertically, gravity is pulling down. So what happens? It falls, but it falls at increasing speed. Okay? If I were to have you out there in the courtyard and I lean out the window and drop something to you, and you catch it, that's not bad. But what if it was up on the roof and drop it? It's going to be a little bit faster when you catch it than it was if I was third floor or 85th floor. No, you're not even going to mess with that. It's way up there. Okay? So here's a falling object. Now is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 balls that they just got strung out there? No. This is a time-delayed photograph of the same ball. And what it is, how they set this up, perfectly dark room. Absolutely dark room. Okay? And they have a camera set up with its aperture wide open. Perfectly black room. But then they have a strobe light over here that's going to flash for, I think it's something like 1/100th of a second. Or every 100th of a second it's going to flash. And the camera's got its aperture open, so the first flash of the ball is here, the next one is here, here, here. What do you notice about that? Now, the same time interval between every one of those flashes.
Speeds up.
Say again?
Speeds up.
It speeds up because gravity is, what do we call that? The acceleration due to gravity. It's speeding it up. Okay? A net force pulling it downward. So sure enough, the distance here gets a little wider every flash. Now, if it's 100th of a second, it's not a lot of difference, but it is something. You can tell there is something. So that's what's happening with falling objects. Now, I said it was released from here. What if I had been under here with a perfectly timed gun of some nature that I fired the ball up? How would the picture look? No, it'd be identical. Because now if I fire it up, gravity's pulling down, slowing it down as it goes up. Now I have to have it timed perfectly so it stops right there. Doesn't bang into it or fall short of it. It would look identical to that. Because gravity always is pulling downward, whether the motion is up or down. Okay? So, here was a formula that was first developed by Galileo. Now, he did it with his inclined planes, and he was able to measure this and say that the distance traveled is proportional to, remember that proportionality symbol? Proportional to the time squared, the square of the time that the motion was happening. And what was his proportionality constant? Happened to be 1/2 a, and that a was the acceleration due to gravity. Okay? We now call it g, 1/2. Now, this is a very special formula under very special conditions. Number one, we're saying the original position is 0. So the distance from when you release it is 0. Because otherwise, if you were measuring the distance from the floor to here, then it would have to have a distance to start with. You would have to have what they call a D0 here, an initial position. But with the initial position 0, that works. But there's another special case. He is releasing it from rest. And what does that mean? Say again? Dropping it. What does that mean?
Acceleration.
Okay, so what is zero? What is it?
We did it on
Yeah, we did it in lab.
I forgot what
Initial
initial
velocity was zero. If he threw the ball down, then you have to have another term in there because it's going to be going through, right? But when released at rest, if you threw the ball upward, then it's going to have even, the distance traveled is going to be different than 2 because you had an initial velocity upward. So this is true only if the initial position is 0 and the initial velocity is 0. Now, if you had an initial velocity there, you multiply it by time. The acceleration is multiplied by time squared. Now, why do you reckon that's the case? Initial velocity would have what kind of unit? Give me an example. Velocity. Say again? That's time. You used it in lab. What's your velocities? Speeds. Say again? You may be saying, I can't hear well.
Okay.
The one in lab. We measured the length of that track in centimeters, and we measured it in
Per
time, seconds. So what was the speed? Centimeters per second, exactly. So if you want this to be centimeters, the distance is measured in centimeters, but you had an initial velocity that you gave it in centimeters per second, you're going to have to multiply by time so the seconds cancel out to give you a distance. Now the initial displacement, that was just so many centimeters. You don't need to multiply. But acceleration, what was its units? You remember that? What were units for acceleration? I told you I've never seen a square second in my life. But
per second.
yeah, per second. So since this is centimeters per second, or per second squared, you have to multiply it by second squared for those two to cancel out, so you do have centimeters. Units are your friends. Pay attention to them. Let them guide you through your problems and make sure they're right. So this is Galileo's formula that if you release something and you have vertical falling objects, we call this free fall. There's a reason for that too. This is the way that it's done. If your initial position is 0 and your initial velocity is 0, that's the formula you use. Okay. Now let me just give it to you since I'm talking about it. If you had initial velocity, you do V0t, and if you had initial position, you would just do D0. Okay? That would be the most widest range of distance formulas. But if your initial velocity is 0, initial position is 0, then you can just forget those and it'll be 1/2 at squared. Okay. And in your text, you'll see Galileo dropping 2 masses off the Leaning Tower of Pisa. It isn't leaning too badly, but it will a little bit. Okay. Now, why we call that free fall, we're saying under no forces other than gravity. That's why we call it free fall. Now, you know if you're anywhere on the surface of the earth, you're going to have a little bit of air resistance. Maybe not a lot. Like, I can stick my hand out here. I don't feel much force on my thing here because my velocity's slow enough. We're going at 60 miles an hour. Yeah, I feel it. Okay. So if your speed is low enough, you can usually ignore air resistance. And most of the things we're going to be doing in this class, yeah, we're going to ignore air resistance. I'm not very fast at anything. Okay, so don't have to worry about that. All right. Let's go back to Bernoulli's effect. I meant to say this, but I forgot to. Have you ever been driving on the interstate? This may be hard for y'all to imagine. When you're just maybe have gotten on and you're going at a relatively low speed and hear this big transfer truck goes roaring past you, yes, you get pulled in. Why? Because the air going around him is going at a much greater speed. That greater speed reduces the pressure. You get yanked into it. You have to watch it sometimes. I mean, you can literally get sucked into his weight. But on the other hand, what do the race car drivers do?
I guess they like the car.
Yeah, and that's why there's multiple ones on the team. Because what do some of the not the stars do? They get out there and the honchos draft on their teammates, right? And that way they're using that Bernoulli force. I'm sure they know that, and that's what they're doing. They're drafting, and you can do it. Not a good idea to do, but on the interstate, you can get better gas mileage if you're able to draft on some of those objects moving about the same speed that you want to. If you're on them. What does the term bird brain mean to you? Huh?
I guess it means simple.
Simple? Well, actually, birds are not that dumb. Have you ever seen geese fly? What's typical of their formation? The V. And usually what's happening there? The one in the lead goes for a while, but when he gets tired, he pulls around, someone else goes up. Because all those behind the V, they're drafting on the ones ahead of. So they're overall conserving a lot of energy doing that. Just the guy out front, he's having to do most of the heavy lifting, but when he gets tired, he comes to the back and drafts on them. And they do that. They do that constantly. So they ain't so smart, but so dumb after all. Not quite so simple. Okay. All right. And by the way, did y'all watch the Olympics? What was it, last month? Not much, a little bit. The speed skaters, they did that. You'd say, this is speed skating? They're going around, not very fast at all, but they're all trying to draft on one another. And actually, when runners do it, you'll have someone set the pace, and they almost never win the race because the others are drafting on them. It's the guys hanging out back toward the end of the race, then they give it a kick. That poor guy up front, he's used it all facing the air resistance by himself. And they show in bicycle racers here in the picture on a closer look, bicycle racers' edge, they do that like crazy. Same thing with race car drivers. Okay. They have a little blurb in the book. They're doing several steps. Step 1, 2, 3, 4. This is on page 36. The whole reason they do that is to explain the 1/2 here. Okay? And what they say is probably pretty close to true, but in reality, where that 1/2 comes from, and none of you have had calculus, have you? Okay? That is what they call the integration constant. In fact, you'll see this in physics. In most of the things we do, there will be one example you won't see. When you have your variable squared here, you almost always have the 2 in the denominator here. It comes as an integration constant, okay, when you're doing calculus. And Newton had to develop this to come up with why planets move the way they did, and sure enough, that comes out in the picture. Now, what they say in the book is true, and there's a way to describe it, but in reality, it comes from that. But you'll see there'll be one instance where you'll have a squared term there without a 1/2 in front. Every other one you see, you'll always see a 1/2 in front. And it comes from that integration constant. So I'm not going through that equation. This is equation 2.4, but I won't go through how you get it because it is good set of mathematics there, but it's really not where it really comes from. So, okay, free fall. Now, I mentioned this before. We call it free fall because it's falling under the influence of gravity without taking into account air resistance. Now, if that's a sheet of paper, you got to take it even at very low speeds. You have to take into account because you got so much surface area there. Okay, but if you're going at fairly low speeds and you have fairly small surface area, you're not going. You can usually ignore it. I've never done any skydiving, nor do I want to. But have you ever noticed people who do skydiving? What do they do when they jump out of the plane? This? No. They become bullets, okay? What do they do? This. So they get as much surface area as possible. I have too much, okay? And that keeps them from hitting such high rates of speed. Now, before they reach the ground, what do they do? And why do they do that? Because now look at their surface area. The parachute is enormous. So whatever speed they're doing, they got enormous amount of air. That goes more like a sheet of paper there. So now they're slowed to a much slower rate of speed. Okay. So free fall is falling under the influence of gravity without taking air resistance into effect. Now, there was a fairly famous experiment done on one of the Apollo missions. I don't think it was the first one, it was a later one when they actually walked on the moon. A guy went out there, one of the astronauts, with a hammer in this hand and a feather in this hand. Dropped at the same time. What happened? Say again? They fell, they hit the surface at the same time. Why? No air on the moon, so there was no air resistance there. On the Earth, that's not going to happen. Okay. So on the moon, there was no air, so they fell at exactly the same rate. Aristotle, you missed it. You never went to the moon, did you? Okay. Never mind. Okay. Now, under free fall, distance is proportional to time squared. We saw that right here. Distance is proportional to time squared. The proportionality constant is 1/2 the acceleration. Okay? Speed, though, increases linearly with time. And if you think about that, that kind of makes sense. V, and if you remember your formula, did we do this formula before? See, I'm teaching a physics class and this one. We're covering some of the same material, so I can't remember for sure which one we did. But speed is velocity times time is going to give you distance, right? Okay? So it increases linearly with time. The t is to the first power. With acceleration, the t is to the second power. That's time squared. The trajectories exhibit the identical up and down symmetries. That's why you couldn't tell whether the ball was thrown up and just happened to come there, or if it was released from rest. That one's released from rest. Okay? But the trajectories are the same. Now here's a rather sobering ramification of that. Now hopefully we don't do this much in this country, even though we have an obsession with firearms. But a lot of the places where the real wackos live, when they're out there celebrating, what do they tend to do? Fire into the air. Okay? Now, get this. Because of the symmetries, up and down symmetries, as you fire into the air, what's about the muzzle velocity of a weapon? Give me an approximate. Anyone know? Would 600 miles an hour be too great? 300? 200? What? I mean, give me something. Say again? Okay, 2,200 feet per second is that bullet leaving the muzzle, right? Is that what you're saying? Okay. So, you fire it straight up into the air. Okay? Dumb thing to do, but you do. Now, we haven't gotten this yet. Oh, let's get a little more date. Hold on to that thought. And that number too, I'll forget it. Okay, here's that formula again. Distance is proportional to time squared. The proportionality here replaces the equal 1/2 A. Distance is proportional to time squared. Okay? All right. Here is the A. If we're in the metric units, the SI units, we're using meters and seconds, then that A is 9.8. The units for it, because that's an acceleration, what would they be? Meters per second squared. Okay? Meters per second squared. That 9.8 is constant anywhere on the surface of the Earth. From the way down deep in the Dead Sea, which is several hundred feet below sea level, to Mount Everest, which is 58,000 feet or something above sea level, the acceleration due to gravity is pretty close to 9.8. May vary a slight amount, but not very much. Okay? Everywhere on the surface of the Earth. So whether you're on top of the building or down there, it doesn't matter. Okay? And the distance that it falls here in 1 second only falls 4.9, because 1/2 of 9.8 is 4.9 times 1 squared is 1. Distance it falls after 2 seconds, 2 squared is 4, 4 times 4.9 is 19.6. In 3 seconds is 3 squared, which is 9 times 4.9, and that's 44. Look at this. Every time it's going further. Every second it's going further. Same as the pool falls going down. They're getting further down. Okay? If you were throwing it up from the ground, it would be slowing down, going less distance on the way up. Okay? That's the trajectories. Okay. Now that shows distance proportional to time squared. Further distance according to the square of the time. Whereas velocities, it goes linear with time. After 1 second, 9.8, here's the formula. V final is AT, where A is still 9.8 meters per second squared, times 1 second is 9.8 meters per second, times 2 seconds would be 19.6 meters per second, 3 seconds. Just multiply linearly. So it goes the same increase of speed every second. Increases though, because it's an acceleration, increasing per time. Okay? Now, all objects accelerate at the same. And the trajectory is the same up and down. So now that we've introduced this, let's get back to our board. What did you say it was? 2,200 feet per second. So we probably should go to the U.S. customary unit, which would be 32 feet per second squared. So 2,200 feet per second is the velocity here. You fire it straight up. In 1 second, it decreases by 32 feet per second. So 2,200 minus 32. A little bit of change, but not much. Then the next second, drops again, 32 feet per second. Then drops again, 32 feet per second. So it takes quite a few seconds for it to get to the top. But at some point, you keep subtracting 32 from 2,200, and after so many seconds or minutes or whatever, it finally has come to a stop. But then what does it do? It starts falling down. And every second it falls, it picks up 32 feet per second each second. So what's the speed when it gets right back up out here? 2,200 feet per second. Yes, because the same amount that it slowed down going up, it is speeding up coming down. Now, this is ignoring air resistance, and of course you've got a little bit of air resistance. And also is this, you said a 22, which has rifling, so you get the spin. You know, that's what rifling does for you, and that makes it do like a spiral football, right? The American football. Okay. So you have that going on, so you get a little bit better. On this way down, it may be tumbling and doing things, so it may slow down a little bit. Okay. But basically, it's just about the same as doing that. If you fire it straight up. But even if you got it at an angle a little bit, that kid over there that's just standing in the wrong place, it's like you shot it directly. Because the bullet is going to come down with about the same speed maybe not exact, close to the same speed, even though you fired it up in the air. Now this, shortly after my wife and I moved to Birmingham, it was, I think, the next fall, maybe 1 year later or something, we read about a couple who had a club cab pickup, and they had their little kid in the back seat and in the child seat, and all safe, exactly like they were supposed to. They were going down the interstate, and they heard something, but they thought it was just a truck throwing a rock or something like that, but they didn't pay any attention. They glanced at the kid, seemed to be asleep. What had happened, someone was either hunting or target practice somewhere in a field somewhere and shot into the air, and just by chance, that bullet came through the back of the windshield right into the kid's head. He wasn't sleeping, he was dead. It was sad, sad thing. So anytime you fire a bullet into the air, it's coming down somewhere at just about the same speed that you fired, 2,200 feet per second or whatever. And that can do damage. Okay? So, never a good idea to be firing these randomly. So when you're target practice, you know you've got a berm there you're firing into. You're not just randomly going into the air. Okay, sorry, that's enough of that. So, I think I don't know what's supposed to be there. I think we're just about ready for example 2.7, and that's maybe why they had the blank here. A rock that is dropped into a well hits the water in 3 seconds. Okay? So what 3 second a measure of? Time. That's your time of 3 seconds. Okay? It's 3.0 seconds, meaning it's exactly to the nearest tenth of a second, 3.0 seconds. Ignoring air resistance, and that's probably pretty sad, how far is it to the water? Say again?
You talking about after you heat?
Say again?
After you heat?
Okay, you drop it into the well. When you hear it splash, it's been 3 seconds. Okay, how deep is the well? Can you figure it from that? Say again? Okay, if you're using 32, then you have D is equal to 1/2 AT squared. And if you're using 32 feet per second squared, that would be 1/2 32 feet per second squared times your 3.0 seconds squared. Okay? Well, I'm going to do half of 32 and make it 16. 3 squared is, so that'd be 16 times 9. But when you square, you also square the units, 9.0 seconds squared. You square the number and the units. Oh, and this was in feet per second squared. Second squares cancel out. 9 times 16 is what? 144? I believe that's right. 144 feet. Okay? Now, what's the other number we use for A or for G? 9.8. So if you use that, then it would be D is equal to 1/2 9.8. What units is that? That's meters per second squared times 3 squared. Sorry, I ran out of room there. Oh, let's do 1/2 of 9.8 is 4.9 meters per second squared times 9.0 seconds squared. Again, the second squareds go out, and 9 times 4.9, that would be 44.1 meters. Okay? Now, those are basically the same distance, because if you divided that by 3, that would be just under 50 yards, right? And a meter is just a little bit longer than a yard, so 44.1. Yeah, that makes sense. Okay? Now that would be almost half a foot. Yeah, almost half a football field. Not quite. Close to half a football field down. Okay. Pretty deep well. Okay. 144 feet or 44.1 newtons. Now they were going to leap round it to 44 newtons because you only have two significant digits here, and the 9.8 is two significant digits, so they don't use the 0.1, they round it to 44. And that's close enough. 0.1 meters is 10 centimeters, that's not very far at all. So 44 meters. Okay. Now, they also go through this thing of average velocity and final velocity and that kind of stuff. So if you want to do it that way, you certainly can. This way is much more direct. Okay. Got it? Any questions on that? Okay. Let's get to compound motion. So there's three types of motion. They don't have the same order we did. There's horizontal motion, there's vertical motion, and then there's a combination of the two. Now when you have the combination of two, that means while it's going this way, it's also either going up or going down. So now you're in a curve motion. Does anyone know what that curve is called? A parabola, exactly. Okay, it's parabolic motion. And you do this too. Have you ever, I haven't watched one of the sniper movies, but if you have, you probably realize those guys take into account, because even that bullet at that 2,200 feet per second is still under the influence of gravity, and for a very, very long shot, which those guys do, you're going to have a factor of gravity. So they've got to aim high. Now, usually they set the scope a little high, so they do it, but they, all those are calculations that are made. I was my third year in the Navy, I was the gunnery officer on an ammunition ship. Now, we had just two very small gun mounts, but we had fire control technicians that calculated and had their computers calculating the thing, and they had to take into account gravity, okay? Because anytime there's motion that is not just horizontal, even a horizontal motion is going to fall, okay? So we sometimes call this projectile motion. An object is thrown into the air, shot into the air, somehow goes into the air. Basic observation. Gravity acts all the time. It's acting when the ball's going up, or the object's going up, the bullet's going up, the projectile's going up. It acts on it when it's coming down. Okay, it's acting all the time. The acceleration, g, due to gravity, is independent of the direction of motion. It's always 9.8 meters per second squared, down. 32 feet per second squared, down. Always. Doesn't matter if the ball's going up, down, or at an angle, the acceleration due to gravity is always down at the same rate. Now we're assuming you're not firing it so far it's going to leave the surface of the atmosphere of the Earth. That, no, if you fired it that far fast, yeah, that things change. So here are the characteristics of projectile motion. A vertical projectile, one that's fired straight up, slows down as it's going up, stops at the top that we described before, and speeds up as it comes back down. Accelerates downward. It's always accelerating downward. Slowing while it's going up is an acceleration downward. Okay? The force of gravity acts on downward throughout the motion, whether it's going up or coming down or stopped at the top, gravity is pulling it down. Now, horizontal projectiles, okay? Have you ever tried to, say, throw a football or baseball or anything and throw it straight horizontal? I mean, you throw it exactly horizontal. If you do that, it's going to hit the ground probably, or at least dip before the receiver ever gets to the receiver, because gravity is always operating on it down. Okay? The horizontal velocity, that part remains the same, but gravity is pulling down, increasing the vertical changes speed all the time. Taken with vertical motion, you always have a curved path. Now, I don't know, baseball fans, have you ever noticed the pitcher's mound is elevated? So even though they're trying to throw horizontal, it's always acting under the force due to gravity, so it's going to be going down. Now, how would you talk about the speed of a curved ball versus a fastball? Okay, speed of it. Typically. Okay, much slower than a fastball, right? And part of the reason there, because a curveball is moving slower, so it's going to have more drop because it has more time for the thing. So it's not that the pitcher is somehow managed, though he's got something to do with it. The threading of the ball and that there's something there that really does contribute to that. But the main thing is gravity is acting on it more. A fastball has less time for gravity to act, so it doesn't drop as much. So yeah, there's always a curved path. Ever shoot a basketball? Parabola. Goes up and comes out. Okay? Golf swing. Goes up and comes out. Always a parabola. Okay? Even a tennis goes up and comes out. Very little change there because usually it's hit fairly straight, but it still will come down. Now, here is something you might find hard to believe. The gal here has a bow, and she's going to fire this arrow horizontally, perfectly horizontal. The guy standing next to her is just holding an arrow, okay? And the instant she releases the bow, he releases the arrow. Which one hits the ground first? Same time. If they released it exactly the same time, gravity is acting downward on this at the same rate it's acting on this. This just falls here. The arrow goes much further here, but time-wise it hits the ground. As long as it's a nice flat level ground, it's going to hit the ground at the same time. If she's firing perfectly straight, he's holding perfectly straight and drops it same time. Because the acceleration due to gravity is the same on each of those. Okay? It's just his doesn't have any horizontal displacement. Hers does. Now look at the horizontal motion. Whatever speed it has in the horizontal direction here, it has the same here and here and here, because neglecting air resistance, those speeds don't change. Of course, his was zero horizontally. It just has the vertical. The vertical is the same in both cases. They actually do strike the ground at the same time. This is something that's really hard to do, but if you could do it, if you were firing an arrow or a weapon or anything at some object in a tree, way out there, and at the very time that you pull the trigger or release the bow or whatever, that starts to fall, then you should aim straight for it where it is, because it's right, it's falling, the bullet or arrow or whatever is going to fall the same way. If it's not, you have to aim a little high, because otherwise your bullet, if it's not released at the same time. So there's the question. Weird but true. Okay. Passing a football. Do they have the, let's see, we already did that. Yeah. Here's the quarterback. No matter how hard he throws, he's got to have some arc to it. He's not going to throw us what they call a clothesline or a second?
Line drive.
Line drive, yeah. There's no really such thing as a line drive. They're all going to fall. They're all going to fall. And so he has to have a little bit of an upward thing. Otherwise, the guy's catching it around his knees or something. Okay? And you see that happening too. So the only force acting once it leaves his hand. Now, as it's in his hand, he's giving it a horizontal and a vertical velocity. But the instant it leaves his hand, he has no more influence over it. He's not forcing it at all. The only force acting on it is gravity, pulling it down. There is some air resistance, but we're neglecting that now. Okay? So as it goes up, he gave it an initial velocity, a component upward, and a component outward. The horizontal component never changes, okay? But the vertical component, he gave it pretty solid one to begin with. After a second, it's reduced. Sometime up there, it's gone to 0, and then at the same rate, it decreased here, it's increasing here, so it's going to come down. There's your parabolic part. Same thing with basketball. Now, the only thing about shot in basketball that doesn't affect the switch. Yeah. I can't do it. I don't. Okay. There's no vertical component. I can't do it. I can't jump. Okay. Never mind. Wait. Okay. All right. The combination of the two motions always forms a parabola. Y'all run into parabolas anywhere else? This is beside the point here, but it's true. A parabola is a shape, a curved shape, okay? And it has this characteristic. Any parallel rays coming in and hits a parabolic shape always going to go to the same point, and that's going to be called its focus. Or, on the other hand, any light leaving from the focus, when it hits the parabolic shape, it exits very close to parallel. Okay? Any of you ever experienced a parabolic shape? Any of you ever operated a flashlight? You know that curved silver mirror? Behind the thing. The bulb is located at the focus. That curved mirror is the parabola, and your beam comes out in your parallel. All right? Okay? Any of you have a satellite dish at home? If you notice, it has a curved shape to it, paraboloid, by the way, because it's 3 dimensions. And then they have a little receiver sitting right out there. Guess where that is? At the focus. So the parallel beams come, because that satellite is so far away, the beams are basically parallel coming in. They hit the mirror, and every one of them heads toward that focus. That's where the receiver is. So you're picking up signals a lot around. Otherwise, it would be such a weak signal you couldn't see or hear anything. But it gets all those considered. Now, you guys, I thought were going to pipe right in headlamps on your car. Curved shape, parabolic. Because the bulb is located at the focus, light leaves the bulb, goes out almost parallel. Now, why I say almost, if that was a point source of light, it would be parallel. But the light bulb is not a point source, it has a certain volume to it. So some of those points are not going to be on the focus. So that's why you have a little bit of spread. But not very much. Yeah. Okay. Those are parabolas. Okay. All right. Yeah, we got it covered. We are through compound motion. That's what we needed to cover for the lab today. So what we're going to go on and do now is start on the 3 laws of motion. This will be on Tuesday's lab. But Tuesday's lab is going to be more than just the 3 laws of motion. It's also going to be the next thing in the book, which is momentum. So we're going to talk about momentum and the 3 laws of motion on the next lab. Today's lab is going to be compound motion, which we just did. So this is stuff that's heading toward Tuesday's lab. 3 laws of motion, first detailed by Sir Isaac Newton. Now back here, I meant to say this before, I may have said it before, back when we first mentioned them, we said Galileo and Newton, okay? This is, to me, a little bizarre, but it's reality. Galileo lived down in Pisa, Italy. Okay. Got into some trouble in his lifetime because he was such a good scientist, and he was a pretty good engineer. He must have been too, because he heard about this guy somewhere up in Netherlands or Belgium or somewhere up there who had made the first telescope. Oh, that sounds good. It magnifies things greatly, especially heavenly bodies. So he got all the details he could, and then he made one that was like 10 times better than that guy had made. And he was looking out at the night sky and happened to zoom in on an object out there we call Jupiter. Anyone know what Jupiter is? It's a planet. Second?
Ball of gas, isn't it?
Yeah, pretty much. It has a solid core. But yeah, its exterior is a ball of gas. It's by far the biggest planet out there in our solar system. I mean, it's humongous, okay? So even though it's a long way away, he could see Jupiter pretty well. And guess what he also saw around Jupiter? 4 moons. Now, I don't think he saw the great red spot yet. That is a storm that's on Jupiter that's been going on for centuries. Maybe he could. I don't know if he could see that. Maybe he could. But he saw the 4 biggest moons of Jupiter. Jupiter only had like 72 moons or something like that. It's just enormous, maybe 52. It's a huge number of moons. But he saw the 4 biggest ones. And they are to this day called the Galilean moons. That doesn't mean they're from Galilee. It means that Galileo first discovered them. And that got him to thinking, wait a minute, if these moons are going around Jupiter, then maybe our moon is going around us. And maybe that means that the sun isn't going around us, and that the stars aren't going around us, because up to then, people thought the earth was the center of the universe. And everything revolved around it, because you see the sun rise, the moon rise, the stars rise, and they go across the sky and they set. Seems like everything's moving around us. Not, he said, if these things would be, and he could see also that Jupiter was spinning, maybe because of that great red spot, which is that storm on Jupiter. And he said, hey, if they're spinning, maybe we're spinning. And that's what makes it look like the sun's going around us and the stars are going around us. Well, that wasn't a very popular view. Remember where he lived? Italy. Now, there's a guy who came up with it a little bit ahead of him named Copernicus. He lived up in Poland or somewhere, okay? Long way from Italy, okay? Now, Copernicus happened to have been a monk, but the clergy were the most educated people of the time, and he had determined, yep, the sun is the center, he said, of the universe. The sun's the center of our solar system. We're revolving around it. The moons are revolving around us. The stars are just moving, seem to be moving because of their relative, because we're spinning, okay? Galileo had run into that too. Okay, enough about that. Well, what was the problem? Copernicus, up there in Poland, he had all these thoughts, he wrote them down, but he wouldn't publish them because he was a monk. And the church, located in Italy, very strongly felt we were center of the universe, okay? And they weren't about to hear any different. So he didn't publish his, but he actually told his assistant that after he died to burn his notes. Well, after he died, the assistant published his notes, okay? They came up with it, Galileo read it, and said, yep, he's right, I've seen it. Yeah, I've seen results of this. That explains everything. Because they never could figure out why the planets didn't follow the same pattern as the stars, or the sun, and the moon followed a different thing. When you came up with the sun being center of the, everything made sense. Okay? Well, why I got into that, I was just telling about Galileo. He got in trouble because he supported that. He lived in Italy. Pretty close, I mean, just a few 100 miles maybe from the Vatican. And he got put under house arrest. He was such a great scientist, they weren't going to kill him for that. But he came that close. So he was in house arrest until he recanted. And then he recanted with his fingers crossed and still wrote supporting it. And after he died, they published all his stuff. But anyway, that was Galileo. The year he died, that Christmas Day of that year, Isaac Newton was born, up in England. So they never interacted except Newton read Galileo's work. But I swear, it seems like it was a cosmic tag team, because the very year he died, Newton came along. Okay, now why did I go into all that? Well, because I'll get there one of these. There it is. The first law of motion that we're going to hit in just a minute, basically Galileo had laid it all out. He didn't have it formally done, but he had laid it all out there. So Newton took that one, built on it, and came up with the other two as well. So that's why we call the three laws of motion Newton's three laws of motion. They weren't really all his. The first one was largely from Galileo. And it's called, by the way, the law of inertia, because that's the thing of an object trying to maintain its motion, resisting any change to its motion, like in the bus or the lawnmower on the back of the pickup or whatever. Now, Newton just didn't change physics forever by these three laws of motion. He also developed a whole new, brand new, from scratch form of mathematics that had never been done before while he was doing that, because he had to explain some of those laws of motion, and he needed to deal with instantaneous velocities and acceleration, not just average. And so he had to come up with a mechanism to talk about instantaneous change, and that was calculus. Okay? Oh, and at the same time, he came up with a whole, no one had really proposed why things fell, and he came up with a whole law, mathematically shown to be quite good, law of gravitation. And at the same time, he did optics. He did an amazing number of things, in one short little lifetime. Okay. Here's a story on him too. Y'all mind stories? Okay. He went to Oxford. No, Cambridge. One of them, I can't remember. They seem very similar. One of the two premier educational institutions in all of Britain. Okay, way up there. But he really couldn't afford it. So what he did, mostly rich kids went there because it was really prestigious. He washed their clothes, cleaned their rooms, shined their shoes, fixed their foods. He was basically a servant of these rich kids, working his way through college. At the same time, passing all of his professors and their knowledge. I mean, he absorbed what they did, put it together, and beyond him, his, you might say, major advisor was a guy named Isaac Barra. As soon as he finished, he stepped down from his chair in mathematics and gave it to Newton, because Newton was way beyond him by the time he graduated. So he was on staff at the university after graduation. And boy, being on staff, I can relate to this. And I'm just at a little community college. But right now, I'm still trying to get summer schedules inputted. I'm still trying to catch up on my grading and all this kind of stuff. Well, Isaac Newton was probably getting sort of swamped with all the responsibilities that came with being a chair. But an unusual thing happened, usually not a very good thing to happen. The bubonic plague, the Black Death, hit England. And here they were. Cambridge and Oxford are pretty close to London, I think. I know Cambridge is. I think both of them are pretty close to London. And it seemed like the plague hit worse in the city. No one knew why the plague hit. No one knew where it came from. They didn't know how to combat it. All they knew it killed people by the buckets, by the cartloads. I mean, when it struck, it was awful. Okay, so the plague had hit, and they said, "Look, our best minds in the country are here in the city, and it seems like people die in the city. Move them out to the country, get them out of Dodge, out of town, and get them out there where it's not less likely to hit." So Isaac Newton, whose father and stepfather and stuff had a farm somewhere out there in Lincolnshire or something like that, he went to the farm. Now he had all this knowledge he had gained at the university, and he sat and thought. He wasn't a very good farmer, okay? He did too much thinking. But supposedly he watched the apple fall and thought, why does it fall? He asked these sort of dumb questions, but they're really important questions. That's why he developed the law of gravitation. Okay? He had read the papers by Kepler about planetary motion, but Kepler couldn't explain why it happened. He just showed that it did happen. So he came up with a theory, explanation. He had to come up with calculus to do that. He came up with his 3 laws of motion. He studied optics. He studied the spectrum. He did, because the school was closed for 2 or 3 years. And you wonder, if the school hadn't closed, would he have had time to think through all these issues? Would science have taken this huge leap forward in the lifetime of this one man who was capable of doing it if it hadn't been that the bubonic plague struck right there? Really interesting to think about. Okay? The essential idea for all these laws of motion is this idea of forces that we've been talking about. That's why they stuck it in there earlier, but now we're going to deal with it. Okay? So let's go to the first law of motion. Like I said before, this was developed largely by Galileo, and it's called the law of inertia. And did I ask you before we started this what inertia means to you? Did I ever ask that question? What does it mean? When you hear the word inertia, what do you think? What's the first 5 letters in it? Inert. So you think couch potato, not moving, not doing anything. And that's sort of what inertia is. If it's initially at that rest, it tends to stay right there on the couch. Okay? Tends to be inert, tends not to change at all. But inertia also has to do with that fastball thrown by Nolan Ryan. Okay? It's going to try to stay at that same speed, that same direction, unless you have to stick up your catcher's mitt and try to stop that thing. Okay? An object that's in motion, whether it's at state of rest or in uniform straight line motion, unless acted on by one of those unbalanced forces, will maintain that, unless it runs into an unbalanced force. Okay? Another way of saying that, inertia, remember, is that resisting to any change of motion. You're on the bus, and it turns, you want to keep going straight. You're in the car, it turns, you bump into the thing, because you're trying to maintain your state of motion. Okay? That's Newton's first law. Here are illustrations of that. Here's the bus, initially at rest. You're standing there, you're not paying attention, not holding on to the strap or the pole or something like that, and just yakking away or whatever, and suddenly the bus takes off and you fall backwards. Why? Because you're trying to maintain your state of rest when the bus is beginning to move. The heavier you are, the more massive you are, the more you tend to stay where you are. Ping pong balls aren't going to resist too bad. They will roll back some. So initially at rest, when the bus takes off, the person falls back unless you have an unbalanced force. Okay? You're hanging onto the strap or the pole that you're pulling on that to keep you from falling backward. That's Newton's first law, the law of inertia, or the Galileo's law, you might say. Or you're standing in the bus again, not paying attention. The bus is moving in a straight line. You're happy. You've gotten used to that motion. and then all of a sudden it makes a sharp turn. Buses don't make that sharp turn, but they do, and you get thrown to the side. No, you don't get thrown to the side. You're trying to maintain your straight line motion, and the bus basically cuts you off. It pushes you in that direction. Okay? But a force is needed to overcome your inertia and change your direction. And that's the same thing that we have the banking at Talladega, because that is pushing you, the car, inward, so you accelerate inward and make your way around the curve. Those speeds, if that was a flat road, into the fence, every one of them, you know, they couldn't help it. The tires cannot grip the roads at those speeds. Or they slow down enough to make the turn, and that's not very fun race, is it? Okay. Law of inertia, first law. So basically, things maintain their state of motion. In other words, constant velocity. No change of direction, no change of speed, speeding up, slowing down. Maintain their state of motion unless they're acted on by an unbalanced force. Okay? What's in the second law of motion? In order, if you do have an unbalanced force, a net force that's not zero, then you're going to have to accelerate. What's an acceleration? What's the definition of acceleration? Has a delta in it. Yes, change of speed per change of time. Delta V per delta T. You change your velocity. And what's a change of velocity? A speeding up, a slowing down, or a changing direction. It's going to happen. A force is going to cause an acceleration. It's going to speed things up, slow them down, or move them. Change the direction. Now, why did they put this in here? Had we hit the units of newtons before? See, I'm teaching a physics class and this class, and we're talking about the same thing. We may not have done that. Let's go back. Let's do this sort of quickly. Forces are proportional to an acceleration. If you have a net force acting on an object, it's going to accelerate. If an object's accelerating, it's got to have a net force on it. Because if it didn't have a net force, straight line, constant motion, not changing. So, what's the proportionality constant? Okay? We know the units for acceleration. What are they? Typical units of acceleration. Centimeters per second squared. Those are the ones we used in lab. The SI unit would be meters per second squared. Okay, like acceleration due to gravity. Okay? Now, a force is a Newton. Oh, I wonder why it got its name. Named after Sir Isaac. And that's why it has a capital letter. Because it was named after a person. Okay? Whereas meter, not named after anybody. Seconds, not named after anybody. Those are lowercase letters. The units that are named after people, uppercase. Okay? Well, a Newton, by the way, is a Newton is a kilogram meter per second squared. So what's the new component here that wasn't in acceleration? That's ugly. Okay? Kilogram. And what is it that measures that you use to measure kilograms? Mass, exactly. So the constant of proportionality, this becomes F equal ma. That's the constant of proportionality, the mass. And guess what? Mass is related to inertia. A bowling ball has a ton more inertia than a ping pong ball. Okay? Just wipes it out. Nobody's business there. Okay? So there is this equation right here embodies everything in Newton's second law. If you have an unbalanced force, a net force acting on the object, it's going to have to accelerate. And that relationship is multiplied by the mass, you get the net force. Divide net force by mass, you get the acceleration. You can set that up in triangles or circles several different ways. Okay? The proportionality constant is the mass. The more force, the more acceleration. The more mass, the less acceleration. If you have a constant force, you increase the mass, then these are inversely proportional. So it's, as you increase one, you have to decrease the other to keep this constant. So if I have the same force and throw a ping pong ball at you with the same force I do a bowling ball, the acceleration is going to be a lot less on the bowling ball, a lot more on the. Let's make it a tennis ball because ping pong ball is effective. All right, that's Newton's second law. Oh, there it is. I wrote it there, and then they wrote it even better. So let me get mine out of the way. Net force is mass times acceleration. If something's accelerating, it's got to have a net force. If you have a net force, it's going to have to be accelerating. Okay. We will pick up there next time. Isn't it 3:30? No, we go to 3:45, don't we? Oh, yes. You were trying to cheat me out of 15 minutes of your tuition dollars, weren't you? Sorry about that, okay? We got a time to do a little bit more. Here are examples of Newton's second law, okay? In fact, I felt bad we were rushing through this. You give me two other formulas that say the same thing as that one. Two other equations. Acceleration equals net force divided by mass. Perfect. One more. Mass is equal to net force divided by acceleration. Perfect. Okay? So this shows that acceleration and mass are inversely proportional to each other. You increase the mass, you decrease the acceleration with the same force, or decrease the mass, you increase the acceleration with the same force. And this one says the same thing. It's inversely related. Here, force and acceleration are directly proportional. Okay? So, and that's where they introduce what a Newton is. It's a kilogram meter per second squared. Kilogram is mass, acceleration is meters per second squared. Okay? Now, in the U.S. customary, force is pound, and we usually don't break that down into mass because we don't usually use the unit of mass. What would it be if we used it? I think I told it to you before. Little slimy thing in your garden. Slug, exactly. That's not the same, but no. Same word. Okay. Newton's second law. Examples of this. Okay. They really don't have this set up too well here, but I will try to show it. Here's a guy on a bicycle. Okay. Pedaling along. Now, there's always some road resistance, there's always some air resistance. If he's pedaling along and applying a force that equals the sum of your frictional resistance and air resistance, then what's the net force? Zero. So is he accelerating? No. He could be going at a constant speed, that's not an acceleration. And he has to be going in a straight line, that's not an acceleration. So here he goes. Okay? Now, I don't know if they're going to have this right. I don't think so. I think you have to come way over here somewhere. They got it out of order. Or maybe they don't even have it at all. I don't think they do. Okay, if you look in your book, those of you who have books, okay, the next figure shows him on a bicycle built for two, doing the same thing. Traveling, oh, it's a different guy. He has one, the same guy who worked, he changed clothes. It's springtime, he put on shorts. Okay, here he is in long. Okay. So he's on a bicycle built for two. paddling along, going at a certain speed. Maybe accelerated, maybe not, we don't know. But then his girlfriend jumps on. And, well, they stop and left her on. But instead of pedaling like she's supposed to, she just folds her feet up here. So he's effectively doubled his mass. If he's doing the same net force, what's his acceleration now? Half. Because he can't accelerate as fast if he has more mass with the same force. So they did a sort of a lousy job. I think that's what should have been following this. They just didn't, whoever the graphics person was didn't understand what they were looking for. Okay. Let's see if we have time to do the examples here. Okay. This is example 2.8 on page 43. Okay. The mass of, a 60 kilogram bicycle and what's that a measure of? Oh, bicycle and rider. I was going to say that's a pretty hefty bicycle. Bike and rider. What's that a measure of? Mass. That's your mass. Okay. Accelerate at 0.5 meters per second squared. So your acceleration is 0.5 meters per second squared. Good units for acceleration. How much extra force had to be applied to make it accelerate, to go from constant speed to an acceleration? Extra force would be a net force. And what's the formula for net force? Mass times acceleration. So that would be 60 kilograms times 0.5 meters per second squared. That seems like a pretty small acceleration, right? That actually is hard to maintain for very long. And what would this be? 30 kilogram meter per second squared, and that could also be expressed as 30 newtons. Now, I didn't keep up with significant digits there. No, they didn't either. So 30 newtons is going to be fine. Sometimes they are real picky about significant digits. Other times they just ignore them. So 30 newtons. Okay? Now, let's do 2.9. Everybody got that? Need to leave it a little longer? Okay. What is the acceleration? So this time the acceleration is the unknown of a 20 kilogram cart. What's that a measure of? That's your mass. Okay. If the net force on it is 40 newtons, what's your acceleration? What would be, what form of the formula would you use? Say that again? Yes, the acceleration will equal force, net force over the mass, which would be 40, but I don't like to write it in newtons. I want to break it down. What are the basic units for newtons? Kilogram, meter per second squared, divided by mass of 20 kilograms. Units are your friends, don't ignore them. Kilograms cancel out, and that gives you 2 meters per second squared. You talk about an acceleration that's going to be hard to maintain, that one will be, because that's increasing its speed 2 meters per second every second. That's accelerating really fast. Okay? So you're not going to be able to maintain that for long. So 2 meters per second squared. Good deal. All right. Earlier, I may have forgotten to mention it, they had a first law experiment at the bottom of page 41. There was also a science sketch on the bottom of page 40 I did mention too. So I'll let you look at those. Okay. But there will be one. First law experiment. Okay? I'll show you this one. Put a piece of paper there and an object there. Okay? Now what would happen if I were to do a sudden jerk on that piece of paper? Am I going to, just in case, get my chalk so it won't break. What's going to happen?
The object's going to move.
It's going to move. Okay, watch it move. Did it? Not much. Why? The what? Okay. Not dealing with net force here.
Object at rest.
It's at rest. And it tends to stay at rest unless operated on by net force. And there was no unbalanced force to speak of. You mentioned friction. There's a little bit of friction between the paper and that, but not enough to make it move. Now, I've heard of people doing this with place settings of china and crystal. I would never do that. My wife would kill me, but but do plasticware, okay? And have a nice slick placemat under there, or even a tablecloth. Okay, but don't use Mama's finest stuff. You'll be in serious trouble if you do that, and it breaks. And you can literally yank the tablecloth out from under the place setting, and they stay right where they are. But now, if there's a nice big hem or some flowery embroidery on the tablecloth that catches that plate and then drags it off, then you're in trouble. Okay, so make sure it's a slick, unseen tablecloth before you try that. That's why I like to use paper and animal objects that don't cost very much. Okay? And what was the principle there? Inertia. It tended to stay right where it was and resist motion. Very good. Okay? All right. Now, we got time, I think, for one other thing. Let's just at least begin looking at weight and mass. Now, I mentioned this before. Mass is related to inertia. The more mass you got, the more inertia it has. The harder it is to get it moving, the harder it is to stop it once it's moving, okay? So that's why when I was in the Navy, there are all these rules for the road, even though you aren't on a road, for when you're two ships going along, the one on the right has to maintain it, and the one on the left needs to adjust to keep them polite. And you have to obey that. And I think you may have heard the Russians have been playing sort of roulette with the American fleet in certain areas. Actually, this is more in the air over Syria. Their aircraft are not obeying the rules of the road, and they're trying to make the Americans have an incident, and they're laughing at us, because they're carrying out things that they're not supposed to, and they don't want us watching. They're bombing people that they're not supposed to be bombing. But that's another story. So anyway, there are all these things, but when I was in the Navy, there was this one young ensign that was just in a little bit longer than I had been, and he was real fired up and gung-ho, and we were coming into port, and on a big ammunition ship, and there was this little pleasure craft was trying to get as close as possible to take pictures of us. And Jeff said to the captain, who was on the bridge at the time, he said, "Captain, technically, by the rules of the road, that boat does have the right of way." And the captain looked at him and said, "Jeff, in this case, we go by a different rule." Sir, the big boat, little boat rule. Okay? We're the big boat. We're going to do what we want to do. Little boat, they have maneuverability. We don't. So that's the big boat, little boat rule. Measure of inertia. We can't turn on a dime, they can't. That's not really a rule of the road, but he made it up. Okay? Weight is so mass is a quantitative measure of inertia. Basically, how much matter there is there. How much is there there? Okay? Weight, though, has nothing to, well, it has something to do with that. It's the force of gravity acting on a mass. So sure, you have to have a mass, but it's the amount of force due to gravity acting on it. Okay? Pounds and newtons measure weight. Kilograms and slugs measure mass. We don't use slugs, okay? But it's technically there. Okay? Now, here's something to keep straight. When you're talking net forces, that's mass times acceleration. That's the Newton's second law. In an equation, that's it. If something is accelerating, it has to have a net force. If there's a net force, it don't have to accelerate, all that. Now, weight and mass are related by very similar formula. Weight is a force, mass is the mass, and the acceleration you're dealing with now is not from a net force. This is from the weight, so you're dealing with a constant acceleration, and that's g, the acceleration due to gravity. Here on the surface of the Earth, that g is 9.8 meters per second squared, or 32 feet per second squared. But if you happen to be on the moon, that's about 1/6 of that. That would be, 1.7 or something like that meters per second squared. If you could stand on Jupiter, like you said, that's a ball of gases, you can't stand on it, its acceleration due to gravity would be huge. Okay? The sun would be even more so. Mars would be greater than the moon, but less than the others. Venus, if you could stand there, you wouldn't be standing there long, you'd be dead. But you would, it's about the same as the Earth, a little bit less than that. Mercury, if you could stand it, which you probably couldn't, it would be more like the moon almost. So you see, different objects will have different accelerations due to gravity. But as long as you're on the surface of the Earth, it's fairly constant. Okay, so we'll pick up next time with, well, we won't do Newton's third law yet. I've got to find my pencil. There it is. Okay? We've got to do the examples of weight and mass. So we'll do example 210 and 211 before we hit Newton's third law. All right. This time I'm going to do things a little bit differently from what we've done before. Before I've carried, oh no, I don't even have it. I can't do that. Yeah, we're going to have to do it the same way as before. I took the thing down to be copied, but I didn't have a chance to get it copied. She had, no, wait a minute, did I? No, I did, that's right. Wait. I think I do have it. So hold on. Not there yet. Yes. I'm going to make you carry the labs to there. I'm not going to carry them, okay? So, I'm learning. Shoot, I don't, no, she has them down there still. I don't think she did get them copied. I thought we did. I'll get 4 of them. I'll go down and get the others and meet you. Oh, and this time we're not in the lab we were last time. We're across the hall in 252, not 253, 252. Take a break. I've got to get things set apart here. That's right. I left it running. That's right. I did get it on, but it was taking a while, so I left it running. Okay. Okay. All right, we've got it set up, and the first thing you do is measure 10 centimeters up from the bench top. That's where you'll run your first trowel. That's why it says on page 70, ramp 10 centimeters above tabletop. You're not adjusting the ramp, we're starting at 10 centimeters. And that way you don't have to make adjustments to it. Okay? So we'll start there. You'll time it. Start the time when it reaches, and you'll hear it when it comes here, and then you'll hear it when it falls off here. That's your stop time. Read the time, record it here on page 70. Do the 3 times first. Make sure they're relatively close to each other. That means you didn't have one that the stopwatch messed up on or you didn't mess up on. So do that for the 3 times. Once you've got that done, then you calculate velocity. What will be your velocity?
0.
Really? Well, it's not going to be moving.
This ain't gonna. This is we got multiply something.
Well, we can multiply, add, subtract, divide. I guess we could take some square roots. Lots of things we could do. Second? Okay. And how are you using gravity in a horizontal run? Not? Okay. We're going to use it later. Don't worry. How do you, distance divided by time. What's your distance on the horizontal run? 1 meter, which is how many centimeters? 100 centimeters divided by time that you just recorded here. But do the 3 times first to make sure they're all 3 in the same ballpark, and then calculate your velocities. Then your average velocity, that's the v sub x, you add those 3 together, divide by 3. Okay? And then we'll pick up and go from there. So, somebody measure your 10 centimeters high, take your ball, and somebody else have the clock in hand, stopwatch in hand, and determine 10 centimeters off the tabletop. That's where you're going to start the ball. Second, once you've calculated the velocities, you add those together and divide them.
We're going to whoa. Whoa. Simmer down, pony. I need to see. There, you're ready, boss.
3, 2, 1.
Oh, that's too. You gotta let it go to the end of the table to be candid.
I know, but how do you know?
Did you mark it?
Yeah, I marked that. 3, 2, 1.
Hey, I'm up here.
So we doing second time the same. It's
Okay.
20.
Someone got the stopwatch? Okay. So it goes by the sound.
Yeah, 0.91.
Start it when it hits the tabletop and stop it when it rolls off. Move things out of the way. Yeah.
Have you ready?
3, 2, 1.
I'm going to pause the recording for a bit. Remind me to turn it back. All right, the next thing after the average of 3 velocities, they're measuring the height of the tabletop from the floor. Okay? Have all 3 teams done it? Take it this team hasn't? We still have. Oh, you did?
Because there's a sniper in the studio, and that makes a
Okay. Okay. All right. Now I'm going to turn the recorder off because, okay. So they calculated their delta x by the square root of 2 times the delta y that they measured times the v sub x that they calculated squared. Divide that by g, but the g needs to be in centimeters per second squared, so that's 980 centimeters per second squared. And they take the square root of that whole thing, and that gives them the delta x. They check that with their cups on the floor when they measured delta X, see how close they got. And then, now they're moving on to 20 centimeter release point, and then ultimately we'll do a 30 centimeter release point for each time calculating the delta X for each of those. Okay, I know some teams are still taking measurements at 20 and 30 centimeters, but for those teams that have their calculations made at 20 and 30 centimeters, what you're going to do now is turn to page 68, make a graph with the velocity on the horizontal axis and the distance on the y-axis. Okay? Use the average v sub x for your velocity and the average delta x distance from each table as the data points. Okay? Now, I want some of you to tell me what those, your typical v sub x's are going from and to. Right, okay, the velocity, v sub x. What were they? You had three measurements. What were they? Okay, something fairly close to that? Yes. Okay, so 20 to 70? 80? Okay. And then what were your delta x's? The very bottom thing? Oh.
I just told you this.
Oh, okay. So v sub x first. Read the v sub x.
69.4, 148.1, and 176.2.
So 60 to 180 approximately. Okay? And what were your delta x's?
20 to 80.
20 to 80. So it sounds like to me the v sub x's are bigger range. So therefore that needs to be on the horizontal axis, right? Yeah, the velocity on the horizontal axis. So if you turn to your graph, okay, turn to your graph paper, I would do it in landscape so that your v sub x's are on the bottom and your delta x's are going up this way, right? So turn it to landscape. Okay?
Which one's going?
Second?
Which one's going?
The delta x.
No.
That's on your horizontal and that's and you've got ordered pairs. Okay. Now, you see those numbers again? That's your 30. So starting at what's your lowest one? And it goes up to what? 176. So let's see. 20, 40, 60, 80, 100, 20, 40, 60, 80. Yeah, if you let each of those big blocks be 20, that'll work. And then vertically, what are they going from 20 to 80, 20, 40, 60, 80. Yeah, you can use it this way. So it looks like to me from their data, I don't know if it'll work for yours, if you let each box on the bottom, your v sub x's be 0, 20, 40, 60, 80, 100, 120, 140, 160, 180. Do any of you have v sub x's great? I mean, yeah, v sub x is greater than 180. No? No, that's the first. Okay, 160, that was it. Is that your 30? Yeah, that's your 50. Okay. So everybody got that? On your graph, 0, 20, 40, 60, 80, 100, 120, 40, 60, 80.
What'd you say the top was, same thing?
The top one, I think you can do 20 there. 0, 20, 40, 60, 80. I don't think you go any beyond 80, do you? Yeah, 100, yeah, 80, 90, 100, yeah, that fits. Yeah. So if each big block is 20, I think you can do it. y'all lose, Delta X is again, this is velocity, so that will be centimeters per second. Which is an important thing to note. Okay? Okay, now don't catch it before it goes off the tape. All right, listen to it. Is that on the same range as the others?
Yes, the other one's 153.
What was that?
160.
Okay, those are close. You might want to redo it just to see if it is, because I was afraid he was catching it before. Okay, that's right. Okay. Y'all decide.
We do one more time. We do one more time.
Okay. Up to you. How are y'all doing?
This is supposed to go to
What? You said distance, but it's distance on right hand, velocity on bottom. We got a velocity that was over 180.
You did?
Yeah.
Oh, okay. Sorry about that. Then you probably have to do 30 down here. 30, 60, 90, 120, 50, 80, 210.
Okay.
I just went by that once. Okay. I'm going to turn off the. All right. If all the groups have gotten their graphs done and calculated a slope, when you include the units on your slope, what was your rise? The vertical axis? Wasn't that centimeters? Right? Is that right?
Yes.
Okay, divided by your run, which was your horizontal axis, wasn't that centimeters per second?
Yes.
Yes. Well, if you do centimeters divided by centimeters per second, that's the same as centimeters times seconds over centimeter, right? Invert, multiply, right? Everybody watching this? Okay. Centimeters cancel out. What units do you get for your slope? Seconds. Okay. Doesn't have to be exact, but give me just a approximate value of what you got. Probably a pretty small number, isn't it? It's what? Say again? 2.32? Okay, is that rise over run? Let me see your graph. I thought so. Okay. 0.43 seconds. That sounds reasonable. Everybody in the ballpark?
Yes.
Okay. Now, the next thing to do is number 2 on page 68. It says calculate Ty from the square root of 2 delta y over g. And by the way, if you go back to page 66, you see that first equation there under figure 6.2? Delta y is equal to 1/2 gty squared. Okay? You multiply both sides by 2, you get 2 delta y. Divide by g, and then take a square root. That's exactly what it tells you to do. So number 2 on page 68 says calculate Ty from the square root of 2 delta y divided by g. Now you got your delta y's, right? You multiplied it by 2, right? And what's your G?
G is 9.
Except we're in 980. So make sure your G is 980. Now let's see what units you have. The delta Y is in what unit? Centimeters. No, centimeters. Delta Y is centimeters. Your G is in centimeters per second squared. The centimeters go out. 1 over 1 over second squared is second squared. Take a square root of that. Sure enough, you've got seconds. So that's going to be the right units. You just do 2 delta Y divided by 980 and take a square root of it. Does that make sense? Yay or nay? Okay, what you get? Have you done it yet? 2 delta Y, whatever your delta Y was, divided by 980, take a square root of that, what you get as an answer. Anyone far enough along to do that?
Comes out when I have a second.
Yeah, it does. And that's about what you got on your slide, wasn't it?
Yes.
And they were both in seconds. Now, why would those two be similar?
Because as one increases, the other has to increase.
Okay? Because what you're measuring with 1 is your d sub x and delta x. Okay? That was the x measurement. So basically, that was the time for it to go from here to wherever your delta x was in, right? And your t sub y is the time it took from it to go here to down here. And guess what? Same time. It's just x and y. If it's moving, it hits the ground at the same time. Right? So it should be the same. All right. Now there is. Hey, did you get a copy of the lab? Okay. I'll let you have that one. I already looked it up. You'll need to go with any team. Okay. Okay. All right, now they're asking for a little bit something different on number 3 this time. It says, use the results from your calculation in question 2, that the t sub y is the accepted value, and the value of the slope calculated in question 1 as the experimental value to determine your percentage error. Okay? Now, first you have to do your error. The error is going to be the slope. Okay? Sorry, I should have started the other way. Your t sub y minus the slope. Is that right? No, slope minus t sub y. Okay? Okay, that's going to be the error. Your slope is your measured. T sub y is the actual. If you measured more than actual, you have a positive error. If you measured less than the actual, you have a negative error. Okay? So that's your actual slope. To get your percentage error, you divide by your actual, which is t sub y. So whatever that difference is, divide by t sub y. Okay? T sub y was that square root of 2 delta y over g. Everybody got that? Now, some of you sound like you were getting the times being very, very close. So your percentage error may be quite small. Huh? The same? Okay. Then you must have done a great experiment. They should be really the same. Yeah. But they won't always be the same. And we talked about why they're going to be the same. Same time making the change of x as it was making the change of y. So the ball is the same ball. So it should be pretty close to the same. But if you came out worse or off some, how could you improve? I'll give you a few examples. It might take more repetitions or something like that, measure more carefully, whatever. Okay. You decide whether the purpose of the lab was accomplished or not. I need an answer there. Doesn't matter what it is. If you got an answer, you get credit for it. You leave it blank, you don't get credit for it. So be sure you don't leave any big blanks without something in them. So let me go back and review. Oh, with one exception. Under procedure number 3, you just did it. You didn't have to write anything there. Okay? So you should have answers on page 68. 1, 2, 3, 4, 5. You should have data in the tables, every blank there. That's 9 blanks in every table. And then you should have a decent graph. Okay? And that's what I'll be grading. Any blanks or no grading? When you're ready, I'll take them. Unless you're, and sorry, I'm cheating you out of your tuition dollar again. Sorry about that. And I'm going to turn off my recorder. And please don't trip over the